Hello there. My name is Stuart Clubb. I'm a Technical Product Management Director with the Calypto Systems Division out of Siemens EDA. And today I'm going to ask you the question, high-level synthesis, are you still missing out? So today I'm going to talk a little bit about new markets and new hardware demands, demands to design new hardware by RTL designers. We'll talk a little bit about high-level synthesis, C++ or System C and MATLAB. Talk about how high-level synthesis is raising the level of abstraction along with high-level verification, and how you can be successful adopting high-level synthesis. Changing technologies bring more challenges for design teams, both RTL design and RTL verification. A lot of technology markets have significant requirements for new hardware data processing designs. This is things with new algorithms, but changing specifications, often where the optimal architecture is unknown. These generally tend to be computationally demanding. Real-time requirements are such that they require a hardware solution. Software just isn't sufficient, be it either the processor is too slow or too expensive, too powerful, because you need an energy-efficient solution. The performance per watt is key, or indeed just when you're striving for the lowest possible power of the implementation. We all generally tend to need faster time to market, but not only time to market for the first product, but faster time to derivative products, moving things from process technology to process technology, from ASIC to FPGA or FPGA to ASIC, all require additional engineering work. And typically we find that there are just not enough RTL designers to do the job. So we must do more with the same resources. So in key areas such as computer vision, neural computing, high bandwidth cellular communications, optical communications, image processing, video compression, anything that's these new and complex algorithms that need to be implemented in hardware, this is where we start to see high-level synthesis picking up steam. And why high-level synthesis and high-level verification? Well, RTL design productivity has fundamentally stalled, probably for more than a decade. But design complexity and the demand for new functionality is growing much faster than RTL designers can code and verify. Just need either more people, more resources to do more of the designs. RTL verification costs are increasing. Regressions involve server farms, more electricity cost, more simulation licenses. Now, emulation can deliver good speed at a significantly higher price, and that can get you there with system integration. There's also the challenge of RTL reuse. There's a penalty associated with reusing RTL. Moving to a different process and a different frequency can be a significant challenge in RTL. Imagine being asked to design something for 500 megahertz, and then suddenly somebody changes the process technology and asks you to move to 800 megahertz. That can be quite a challenge. Moving from FPGA to ASIC or from ASIC to FPGA isn't always that easy. And so reusing RTL can often be quite inefficient for quality of results. And we've even seen in the last year or two supply chain challenges that really call for portability to move perhaps between FPGA vendor and FPGA vendor. And being late kills your total profitability. You may spend more money, but so long as it arrives on time, you won't lose much. If your product cost is too high because it's too big or needs more cooling and things like that, well, that's not so good. But being late can basically lose 33% of lifetime profitability in typical semiconductor markets. It's very important to actually be able to do the job on time. However, high-level synthesis and high-level verification is still hardware design and verification. It is not software synthesis. So all of the skills that you have as an RTL designer are still very much applicable. You're just designing the fundamental architecture, typically using a C++ compiler, maybe G++, Visual C++ for your simulation rather than an RTL simulator. Designers then get to focus on the what and less on the cycle-by-cycle register-to-register flows. This means we use bit-accurate modeling. I'll talk a little bit about that in a while. We focus on architecture implementation specifics and the memory architecture, which is the how of how data moves around. Traditional RTL technologies exist in the high-level synthesis and high-level verification space. So if you think of things like code lint, there's a tool called Catapult Design Checker that does linting for your C++ or System C. You've got code and functional coverage. This is driven with Catapult coverage. So not only expression coverage, branch coverage, statement coverage, but also functional coverage, much like System Verilog, but done in C++ or System C. Even formal verification apps that are tuned and applicable to high-level synthesis with the Catapult formal product. So high-level synthesis generates RTL from C++ or System C. Designers no longer have to describe every single register and logical gate in the source. That's what RTL is, register transfer level. This means that the abstraction is elevated and the low-level timing is handled automatically by the synthesis tool. Things like interfaces, weight controllers, back pressure, ready valid data, handshaking, RAM transactions, pipeline memories are all handled correct by construction and are much more abstract. And I'll give you some code examples in a moment. Parallelism and the area and timing trade-offs and again and throughput are all optimized again using constraints within the synthesis tool. So conceptually, we start with some functionality described in C++ or System C. We add the technology library, which is your process or your FPGA target, and then constraints. Frequency is a constraint in high-level synthesis. You don't want to over-pipeline a data path, but neither do you want to under-pipeline it and cause the area to blow up. This goes through Catapult. The constraints drive the parallelism. You'll hear terminology such as loop unrolling and pipelining. And then Catapult builds that RTL, which is current RTL from classes or functions, or indeed SC modules with System C, and adds things like the state machines and the weight controllers and the I/O interfaces. Closes the timing. We'll see a little example of that in a bit. And does lots and lots of resource sharing to get minimal area. Very competitive with handcrafted RTL. Ultimately, you're going to get RTL out and bills of materials, scripts for downstream tools and reports and so on and so forth. Now, you've heard me mention high-level synthesis, high-level verification, but C++ and System C. And the question is, well, which one should I use? The reality is that C++ has become very popular in the high-level synthesis space. It's a methodology where you have no clocks and no resets in the source code. It's sequential by its very nature, the way the C++ is described. And that means that simulation is extremely fast, literally orders of magnitude faster than RTL. So for functional verification, debug, it has a lot of advantages. It can implement what we call implicit concurrency. This uses a technology as KPN or CAN process networks. And fits very well into algorithmic environments like MATLAB and Python, right? MATLAB, you use Simulink, bring back in MEX functions and so on and so forth. Python, of course, really is built on C++. And by being able to experiment with quantization beyond software types, this really helps both algorithm and RTL teams end up with a very good golden reference. However, System C has some attractions and benefits as well. You have explicit modules. It feels kind of more a bit like Verilog or VHDL, explicit clocks, explicit resets, and explicit concurrency. And that has advantages because it makes performance modeling viable before you get to RTL, but still in a significantly faster simulation speed. Another advantage, especially with MatchLib, which I'll talk about in a bit, is a pin-level RTL view that means you can drop the System C view into an RTL simulator and co-simulate it, or maintain the transaction style views at the System C level. You can also write RTL in System C. Everything you can do in Verilog, you can do in System C. You might not necessarily choose to, but you can certainly do that. The good news is that Catapult supports both. So you have flexibility in choice. There's no language option. It just comes supporting both. Because ultimately, System C is C++, just with a bit more hardware-centric stuff in it. I mentioned bit-accurate data types. There are really two different types that you'll see in use today in the market. The AC types, the algorithmic C data types, or the System C types. We typically see high-level synthesis designers and verification teams prefer the AC types. They're very robust. There aren't some of the bad logic issues between types that there are with System C. And the AC types can also be used in a System C design. So they simulate faster, they're more predictable, really great reason to use them, even if you're doing System C. This is especially true for the fixed point data types where you're representing fractions. The AC types are literally, again, an order of magnitude faster. Untimed C++ simulation is also materially faster than System C. You don't have the context switching of threads that are inherent within System C. Those types are both public domain. HLSLibs.org is where we maintain all of our open source IP, as well as the AC types and MatchLib. But of course, System C is also public as well through Accelera. Nice thing about the AC types are they're just a set of header files. There's no libraries to link. You just point to an include directory and away you go. The fixed point types for both include optional rounding and saturation modes. So this is a bit different from what you're used to with VHDL or Verilog. If you want rounding, if you want saturation, you have to describe it in your RTL. These are built in, so mathematically, when everything is synthesized to RTL, the rounding and saturation modes get created. I've mentioned MatchLib, and MatchLib is System C technology that's a library of common used functions and components. It was developed in partnership with NVIDIA Research, part of a DARPA Craft research program, and brings a header file that you use within your System C design for interfaces, FIFOs, interconnect. They've even done work and published work on complete programmable networks on chip and such like, to use through Catapult high-level synthesis. Now, the neat thing about this is that because we're using explicit concurrency and we're using MatchLib, which gives you throughput accurate modeling of IOs within your block, it enables the design and verification of much more complex SOCs and the interplay of data movement within them, such that you can verify the throughput of the system level performance much earlier than waiting to get to RTL. It even has a mechanism to back annotate latency into individual blocks and have a timing approximate simulation that is still materially faster than RTL and still plugs into your DV RTL flows. And that's a big win there, to be able to drive System C designs that you're going to use through HLS still through your System Verilog traditional UVM environment. That really helps to improve control-oriented designs and verification because of that throughput accurate modeling. So if you're doing DMA, arbiters, bus interfaces and such like, there's a huge benefit there. Those are all available through the HLSLibs GitHub. Again, freely available, supported by Catapult, but used for simulation on your own if you like anyway. So why is that important? Well, as designs get bigger and we start addressing SoC accelerators and such like, there are usually huge data sets with large intermediate results. And the hard part is the data movement under all scenarios. You might have a CPU, but you've got a bus system, you've got arbiters, you've got splitters and routers going out to memories. But the memory and the interconnect architecture can have a very large impact on power performance. We can see here, okay, if I've got some simulation where I'm actually doing simulation, one guy needs to read data and another guy needs to read data, they're going to have to wait for each other, even though the bus may be fully loaded. And seeing that in the pre-RTL space can be very valuable, because ultimately evaluating the architecture at the RTL level is really not feasible. You build one RTL and away you go. It's too much work to create lots of architectures in RTL. But if your integration at RTL is where you first find these problems, it's very late, very costly to debug and fix those problems. So by using System C and MatchLib, that integration can occur earlier. You can fix problems earlier, and that's of course going to be far less costly to do so. So high-level synthesis sounds great. We're raising the level of abstraction for both exploration and optimization to implement high-quality RTL. So you'll hear a couple of things about high-level synthesis. An example might be microarchitecture control. The user has control over the implementation through constraints. So things like parallelism, throughput, area trade-offs versus latency are all associated with what's called loop unrolling and pipelining. Memories, so you're an RTL designer, you're used to saying, oh, I need to use a single port memory. I need to use a one read, one write. Oh, maybe I need to split this logical memory up into different physical memories. These are all things that you have to design and actually physically code in the RTL, never mind whether you're going to use something as registers for storage. So exploration and implementation are done by applying constraints within high-level synthesis, not necessarily by changing the source code. Give you a simple example. Here's a multiply accumulate. We'll make n4. Com plus equals data I multiplied by coefficient I. Well, through architecture constraints, maybe you get an implementation that you want, which is just a single multiplier and an accumulator, register for a feedback path. Maybe at high frequencies in FPGA, the multiplier needs to be pipelined. That's all taken care of by the high-level synthesis tool. Or alternatively, maybe you need something that's more parallel. Again, multipliers optionally pipelined based on the frequency and the process technology you're targeting, and then build a nice adder tree or refactor the adder tree based on whatever the DSPs are in an FPGA, or if it's more optimal to an adder tree with CSA in an ASIC. All done work by not needing to change the source. So your simulation, verification all ends up working exactly the same way, irrespective of the final RTL. High-level synthesis will do lots of automatic arithmetic optimizations. The types, both the system C types and the AC types, are mathematically precise. You add an 8-bit plus an 8-bit, you get a 9-bit result. You multiply an 8-bit by an 8-bit, you get a 16-bit result. And those enable the mathematical accuracy to propagate all the way through from inputs to outputs, and for the tools to strip things away. I kind of mentioned and alluded to this concept of multi-objective process-aware scheduling for both FPGA and ASIC. So we're trading off area versus latency by driving that data path scheduling to really eliminate the RTL technology penalty of IP reuse. Again, simplistic example, adding up 8 numbers. Well, okay, you could just write a lot of pluses in Verilog and you'd have everything in one clock cycle. But maybe you're in a process technology where the adders and the routing end up being slow and you need to pipeline them. Well, if you're an RTL designer, not only do you have to pipeline the data path, but you have to take care of all of the synchronization for how data flows in and when it flows out. But you might need something that really is just everything in one clock cycle because you're in a faster process technology and you're not pushing the frequency bounds. Again, same source code, but technology aware scheduling and parallelism aware scheduling. Last thing I want to touch on is the way memories are handled. Memories are inferred from arrays in the source, be it C++ or System C. You can also instantiate memories explicitly, just like you do in Verilog and VHDL within System C. Those arrays are mapped to your own physical ASIC or FPGA memories. So in ASIC, that takes care of all of the BIST, port punching and such like, or you can just map things to flops and register file views. Coding style and memory architecture do matter, though. And here's a quick example of a delay line implementing a circular buffer, something that you would see a lot in image processing, doing windowing and line buffering, maybe things like Com2D in AI and ML. What we have here is a function, delay line circular. It returns a data type and it takes in one data type. So you feed something in and then you get something back out. There's a static storage for the RAM. In this case, it's 256 deep. We're not specifying what kind of memory it is yet. And then we have an index. Now that's static. Now in C++, and when you're using a class-based methodology, these would be member functions or data members, and they wouldn't be static. You just want them as part of the class so it can be instantiated. But this makes it kind of easier to understand the code. We then have a read before write behavior, right? Return value is storage indexed with the index value, and then storage index its data in. So we're describing here a read before write behavior. It means if you're going to use a single ported memory or even a one read, one write memory, you're going to need read before write. you're an RTL designer and you've been limited to single-ported memories that are only allowed to have a read or a write, and therefore the read-write resolution is unknown, and you get X's when you try to do both, then you would need to code the classic trick of using a memory that has double the width and half the height, so still the same physical storage, but then you do 2 reads effectively on one cycle and 2 writes on another cycle. Then we're just indexing and updating that index. In this case, okay, if it gets to 0, take it to 255, otherwise subtract 1 and then just return that value. This is very portable. Go to FPGA, go to ASIC, swap around to your heart's content, use pipelined memories. It doesn't matter. The functionality we're describing is the same. Catapult brings low power, high level synthesis to the market. First off, we have integrated early power estimation with PowerPro under the hood. So by using the process technology and the DV switching generated by the verification environment in Catapult, we can get early power estimates. That means that now you can explore both microarchitecture and architectural choices within high-level synthesis. While high-level synthesis will do memory access minimization, banking and interleaving choices, different physical memories, pipeline memories for performance can be an architecture choice, such that you can evaluate performance, power, and area for each implementation. We also integrate the PowerPro optimizer engine under the hood with Catapult to automatically optimize and further refine the output RTL. And yes, there's a formal verification flow for that as well. And only Catapult has all of that integrated technology. So how can you be successful adopting high-level synthesis? Okay, this sounds good. Maybe I could use this. Well, first of all, pick your target, right? High-level synthesis, as you can probably imagine, yields a huge return on investment in many of these new design areas that are highly algorithmic, lots of data processing, which gives it a major advantage over a traditional RTL design. So all of those complex algorithmic blocks. But even if you've got lots of data moving, there's still an advantage over RTL, the faster simulation, using technologies like MATLAB to be able to actually model the performance of your design, even down to the pin wiggling RTL or cycle accurate complex flow control side of things. Pick the right language for your team. C++ does very well in the pure algorithmic space. We see a lot of customers talking about that, but System C and MATLAB have those design and DV advantages as well. Just work with your Siemens AEs to guide your RTL team on your adoption of high-level synthesis. You won't be first, but you don't have to be last. Right? There have been lots of customers who've talked about their use of Catapult high-level synthesis, from NVIDIA and NVIDIA Research, Facebook, Bosch, ST, all the way through to Chips and Media, Photonation, Horizon Robotics, and such like. So, like I said, you don't have to be last. Siemens delivers a complete high-level synthesis and high-level verification solution, because a lot of the benefit of high-level synthesis is really the verification side of things. You'll read in papers how companies like NVIDIA have reduced their verification costs by up to 80% and such like. So Catapult Design Checker, lint for C++ or System C, Catapult Coverage, doing code coverage and functional coverage, much as in the same way as you would do with RTL, to get the same metrics to make sure that you're actually testing your code correctly before you even get to synthesis. And the Catapult formal technology apps that are aimed at specifically at HLS problems and solutions. Catapult is providing very leading technology such that designers can achieve competitive Q of R and low power RTL in less time with lower costs. So do more and get it done. C++ or System C, we support both, regular System C with the Accelera standard, or indeed MATLAB to expand upon that. And of course, ASIC and FPGA, we don't care. So you can learn more with Siemens EDA. We have our website, we have on-demand training, which you can actually use the tool live with, our HLSLibs.org. So eda.software.siemens.com is the landing page for Siemens EDA, and HLSLibs.org is where we store all of that valuable IP that's open source. So with that said, I'd like to say thank you, and I look forward to your questions in a bit.